polymer matrix composites, we look predominantly at the interface. So because if you combine two materials, you get one and the other in one material, but you also get an additional thing, which is sort of the interface between the two types of materials. And that oftentimes makes or breaks the new material, in a sense that it many times encompasses or houses the function of the new material, but it also constitutes weak points of the new material, and you need to sort of address that, try to research what you can do in order to improve that. So we look at the interfaces, we do it experimentally and computationally.
I'm trying to better understand how composites behave so we can better predict how they're going to fail. And so we can make safer cars and safer planes out of lighter and stronger materials.
I guess we do have a certain way to approach it, which is to combine computation and experiments, and especially nowadays with, or recently with the Materials Genome Initiative, we're sort of right on the dot about predicting behavior and then finding it and designing materials that would obey those predictions, and we could improve the cycle of development and accelerate that using this approach.
Composites are, they're used everywhere, so they're in cars, planes, bikes, fishing poles, everything. And so there's a lot of interest in how to actually accurately model their behavior. In our lab we use laser spectroscopies, Raman and Brolin spectroscopy, and they give me both chemical and mechanical information about the epoxy. And so I try to link those two pieces of information to see how chemistry and mechanics are intertwined in the epoxy and how those relate to their location in the composites.
How do you represent an interface using different approaches? So finite elements, for example, they consider material as a continuum up to the edge of the material, and then it stops to exist. And maybe the next material starts to exist, and you have a discontinuity between that, which is a singularity. And that's mathematically difficult to treat. And so people have developed ways to go about that. But in molecular simulations, you don't have to do that because your representation of matter is discrete in that you represent every atom or at least every molecule. And so your interface has the right structure. It has the surface roughness, the interfacial roughness, the corrugation, the defects that exist there, all of that is explicitly represented. And the exciting part is to combine the two, and that's done via statistical thermodynamics or statistical mechanics. So there's formalisms that allow you to express the same property in two different ways, continuum way and statistical way.
I do atomistic simulations of polymer-non-polymer interfaces. So basically, I look at what's going on at the interface inside of composite materials. As a computationalist, I get to work with some of the most advanced computers in the world. And I get to use them to understand what's happening at a scale so small, even scanning electron microscopy can't see it.
I get to play with lasers in the lab. There's not much more fun than getting to go in, turn on a laser, and see it light up your sample and start doing science on it.
Well, material science students start with the introductory courses like MSE 220, and they come to study material science because they want to make materials eventually. They want to be employed to make materials, develop materials, and use materials in technology. And so why should they be interested in composites? Of course, is you can only get a certain amount of or a certain property from a single material. So if you want a combination of properties that one single material doesn't give you, then you have to combine different materials. That's the approach that you take. And so in order to get the right combination of properties, you will have to deal with composites eventually. And that's probably why they should learn about it.